Okay. What this is really going to lie and be hinged mainly on is the overall distribution of electrons within a molecule, right? So for example, if we had a molecule like CO2, we can draw the Lewis structure for CO2, right? That is the Lewis structure for CO2. Now, if we consider electrons, do electrons like to be around one another? No, right? Electrons, which are present in this bond, and which are present in this bond, what do they do when they get close to one another? They repel, right? So like charges repel one another when they get too close, right? So because of that, the electrons that are localized in this bond will in general arrange themselves so that they are as far away from one another as possible, okay? Because again, electrons repel, and that repelling puts them as far away from one another as possible. So the overall idea, or the overall theory that we essentially utilize in understanding this repelling of electrons is called valence shell electron pair repulsion theory. So we utilize this little acronym, VSEPR, right? So VSEPR is always dealing with us being able to predict the three-dimensional structure of a molecule based on this repelling of electrons, and them getting as far away from one another as possible. I will also sometimes refer to this as VSEPR. I don't think I'm supposed to do that, though. I don't think that's a thing that most chemists do. So it's supposed to be called VSEPR, but again, I will sometimes utilize the word VSEPR. Is there a mouse in here? Okay, sorry. Sounded like it, though. No? Okay. Rats, yeah. Okay, all right. So valence shell, VSEPR. We're just going to call it VSEPR. Okay, so how are we going to be able to utilize VSEPR to predict our overall three-dimensional structure of a molecule? First thing you have to do in using VSEPR is to determine the number of electron domains or electron groups in your molecule. So this word domains, sometimes I will call these electron groups as well. They are synonymous with respect to one another. To do that, you first have to draw the Lewis structure. So it always comes back to Lewis structures, right? So for example, let's say I wanted to determine the three-dimensional shape of something like formaldehyde, which is CH2O, okay? Before I can do anything, I have to draw the correct Lewis structure to determine the three-dimensional shape, right? So how would I do that? I want the Lewis structure. Who's going to be my central atom in this molecule? Carbon. Carbon comes first. It is, for the most part, hydrogen can't ever be terminal, so it has to be carbon. So then I'm going to surround it with my terminal atoms. So hydrogen, hydrogen, and oxygen. What is my next step? I'm going to sum my valence electrons, right? So I have carbon. How many valence electrons does carbon have? 4. Then I have 2 hydrogens. How many does each hydrogen contribute? 1. And then I have an oxygen. How many valence electrons does oxygen have? 6. So 4 plus 2 plus 6 gives me 12 valence electrons. I will now distribute them into my structure. So I've got a single bond, single bond, single bond. What should I do now? Going to go ahead and fill in the outer octets. Do I have to worry about hydrogen? No, it's fine. So 2, 4, 6, 8, 10, 12. Is that it? Am I done? No, because there's a problem with this structure. What is that problem? Carbon does not have an octet, right? So I'm going to take away a little lone pair here, and I'm going to make a double bond with it. Okay, so this is the correct structure for formaldehyde, CH2O. So that's number 1. You need to draw the correct Lewis structure for the molecule. Once you do that, you're going to move on to step number 2, which is determining the number of electron groups or electron domains around the central atom. So when I redraw this, I'm going to be given this guy, okay? Who is the central atom? Because that's what VSEPR hinges on entirely, is everything around the central atom. Carbon, right? So carbon is our central atom. So now we're going to determine the number of electron groups that are around carbon in this molecule. So an electron group or electron domain is defined as a lone pair of electrons, right? Or it's defined as any type of bond. It does not matter if it is a single, a double, or a triple bond. Any type of bond will count as only one electron group, Okay, so for carbon, how many electron groups do I have around carbon right now? So I have, let me highlight here. I have a single bond, that is one. I have a single bond, that is a second one. What about the double bond? What do I count that as with respect to electron groups? Just one, right? So now, overall, how many electron groups are around carbon? 3 electron groups, or 3 electron domains, okay? All right, so let's utilize that in a question. So I want you to tell me how many electron groups are around the following molecules, around the central atoms in the following molecules. Okay, so let's go ahead and go over these. Most of you get the first one right, but then things kind of trail off. All right, so for the number of electron groups around the central atom in methane, so I've drawn out the skeletal structure for methane over here. I've got 8 valence electrons to distribute. So when I do that, I get single bonds between carbon and all of the 4 hydrogens, right? So that, everything's good. That is the correct Lewis structure for methane. So now, how many electron groups are around carbon in this structure? So each bond counts as 1 electron group. There are 4 bonds, so there are 4 electron groups. Okay, so overall for carbon, or carbon and methane, there are 4 electron groups. Now the second one, we've got, what is this? SO32 minus, what is this called? Sulfite, I think, sulfite, okay? So sulfite, sulfur is in the middle. It is surrounded by 3 oxygens. When I sum up the valence electrons, I get 26. Correct me if I'm wrong, 26 valence electrons. So when I distribute, I will distribute 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So that fills in all of my outer octets. What am I going to do with the last 2? Lone pair on sulfur, okay? And then, is this an okay, acceptable Lewis structure for this guy? Does it violate any technical rule right now? No, everyone has an octet, but because of formal charge and formal charge minimization, the better structure for this would be this. At that point, you'd have a -1, a -1, and then sulfur would be 0, and this guy would be 0. Okay, so technically, it doesn't matter which one you draw, you're still going to get the same number of electron groups. How many bonds are on sulfur? So we've got a single bond, a single bond, a single bond, and a double bond. How many electron groups do those count as? 3, right? So an electron group is any type of bond. It does not matter if it's single, double, or triple. It only counts as 1, right? So we have 1, 2, 3. Now what about the lone pair? That also is an electron group, right? So this lone pair also counts as 1. So overall, because of that, we have 4 electron groups around sulfur. And then for the last one, NH3, we get 8 valence electrons, 2, 4, 6, 8. This is the correct Lewis structure for ammonia. So how many electron groups are around nitrogen? We have 3 bonds and 1 lone pair. Overall, that gives us 4 electron groups. So all of them had 4. Trick. Bet you guys didn't expect that one. Okay. All right, so again, lone pair, any type of bond, counts as 1 electron group. Okay, and so with that, now I will stop for today. So we're right in the midst, the overall 3-dimensional structure of molecules. Okay, that's what we're trying to do. We're trying to take these nice 2-dimensional Lewis structures and project them and see their overall shape in 3 dimensions. Okay, so last time I told you the first step of utilizing VSEPR is drawing the correct Lewis structure. Okay, the correct Lewis structure is going to tell you how many electron groups are around the central atom. Okay, so we counted electron groups last time. So just as a reminder, an electron group, so it's an electron group, this is also called electron domains very frequently, is a lone pair of electrons, right, or any type of bond. Okay, so a lone pair of electrons counts as an electron group or any type of bond. Okay, so the first step in utilizing VSEPR is counting the number of electron groups. Now, the second step in utilizing VSEPR is using the number of electron groups to predict the overall electron domain geometry as well as the molecular geometry. And I'll try to specify the difference between those in a second. Okay, so again, VSEPR, the entire purpose of this is, or the theory behind it, is the fact that electrons are repulsed by one another, right? So when they are in a molecule, they want to get as far away from each other as possible, okay? So let's imagine that we have a molecule, something like beryllium dichloride, or beryllium chloride, and we draw the Lewis structure for beryllium chloride, okay? We draw it, we draw it with beryllium with 2 bonds. Why is that okay if I draw the Lewis structure with beryllium, only 2 bonds? Because it's an exception to the octet rule, right? Beryllium is okay with only 4 electrons around it, does not need 8. So that is great. So now I look at this structure. How many electron domains does beryllium have around it, or electron groups? 2, right? It has 2 single bonds. So there are 2 electron groups. And the whole idea behind VSEPR is that these electron groups are going to arrange themselves to get as far away from each other as possible. What is the most optimal arrangement of those 2 electron groups in 3-dimensional space? Completely, directly apart from one another, right? If they can get as far away from one another as possible, it's going to be via this little molecule here, which gives us what we call a linear geometry, okay? A linear geometry will take these electron groups that are in these bonds and get them as far away from one another as possible. In this case, this ends up being 180 degrees away from one another, okay? So that gives us a nice linear geometry. All right, so this is what we call electron group geometry. So for beryllium chloride, the electron group geometry is linear, and again, we have bond angles here of 180 degrees. Now, we take beryllium chloride, it only has 2 electron groups. Let's try to expand that, right? What if we have a molecule that has 3 electron groups? What would be the optimal arrangement of those 3 electron groups to get as far away from one another as possible? Right, so if we move on to 3 electron groups, like what we see in boron trifluoride or boron fluoride, I forget what the name of this thing is, right? So boron is another exception to the octet rule. It's okay not having 8 electrons around it. If we look at the Lewis structure, we have 3 electron groups around our central atom of boron, okay? The most optimal arrangement of these 3 electron groups is all of them lying flat in the same plane and them being spaced 120 degrees away from one another, okay? So all of these bond angles in this structure are 120 degrees, okay? We call this electron group geometry trigonal planar geometry. There's a reason for that. So if we look at our little terminal atoms, what do they form? Triangle, right? So this guy, terminal atoms form the shape of a triangle. And then what do you think the planar comes from? They all lie in the same 2-dimensional plane, right? So they all lie in the same plane of the paper. So this is why we call this trigonal. Okay. Sorry. Trigonal planar. Okay, so that 2 electron groups, we get linear electron group geometry. 3 electron groups, most optimal arrangement is the trigonal planar electron group geometry. Okay, so now what happens if we move on to 4 electron groups? What is the optimal arrangement of 4 things about a central atom to get as far away from one another as possible? So again, most people would say, oh, well, okay, 4 things. If we all draw it in the exact same plane, and we're all in 2 dimensions, which is not the way that we live, what would be the optimal arrangement of this in 2 dimensions? It would be horribly bad, 90 degrees apart from one another, right? Why is 90 degrees not the optimal arrangement in real 3-dimensional space? If we were stuck in 2 dimensions, it would be 90, right? But we're not stuck in 2 dimensions. Instead, we move into 3 dimensions, right? And so the optimal arrangement of 4 groups about a central atom in 3-dimensional space is what we call the tetrahedral geometry, okay? So the tetrahedral geometry, we call it that because the terminal atoms form the vertices of a tetrahedron that takes on this tetrahedral shape. In our little tetrahedral electron group geometry, all these guys are spaced so that they are 109.5 degrees apart from one another, right? So we've got methane as our model of the tetrahedral electron group geometry. All of these bond angles between our terminal atoms end up being 109.5 degrees apart from one another. Okay, this is the optimal way to arrange 4 groups in 3-dimensional space. Okay, and methane makes the perfect example of a nice tetrahedral molecule. Okay. Okay, so that was 2, that was 3, that was 4. What comes next? 5 electron groups, right? So what if we had a central atom that has 5 electron groups around it, which we can, right, because we can expand the octet if we are in period 3 and below. What would be the optimal arrangement for 5 things in 3-dimensional space? So the next one, we move into the trigonal bipyramidal electron group geometry. Okay, so again, this is the electron geometry for 5 electron groups. Okay, so a couple things to note about this. Why do we call it trigonal bipyramidal? So if you look at the actual shape of it, it essentially looks like you have 2 triangular pyramids stacked on top of one another, right? So that's where we get the trigonal bipyramidal. Okay, so in this structure, we're going to have 2 different positions in the overall geometry. We're going to have positions that are called the equatorial positions, and we're also going to have positions that are called the axial positions, okay? So these guys are going to differ with respect to one another. So I'm going to start by talking about the equatorial positions. So if we look here, in this equatorial position, what we essentially have are 3 groups that are situated in the exact same plane that are 120 degrees away from one another. What is that reminiscent of? 3 groups. We look at the equator here in all of these equatorial positions, and we ignore the other 2. What does that look like with respect to electron group geometry that we've already talked about? It looks like a trigonal planar position, or trigonal planar overall geometry, right? And so that's what essentially trigonal bipyramidal is. It's this trigonal planar thing that lies all in the same plane, and then you have 2 things that pop up above and below that trigonal planar position, okay? So everything in the trigonal planar position is going to have 120 degree bond angles with respect to one another, and the 2 things that pop up above and below that trigonal plane are going to be 90 degrees with respect to the trigonal plane, okay? Now, why do you think we call these equatorial? Everything that lies in this trigonal planar thing, why do you think we call them equatorial? If you imagine this molecule like a globe, what would these positions look like? The equator, right? So these are the equatorial positions because essentially they lie around the center of our little overall molecule, okay? We also have the axial positions. So the axial positions are just going to stick up above and below at right angles directly with the trigonal planar equatorial positions, okay? So with trigonal planar, we get both 90 and 120 degree bond angles. Okay, so 2 different positions. That's 5 electron groups. What's next? 6, right? So there is an electron group geometry for 6 electron groups. What would be the optimal arrangement of 6 things about a central atom to get them as far away from one another as possible? So the next thing is essentially just adding 1 more atom to that equatorial position. And we're left with something called the octahedral electron group geometry, okay? So we call this octahedral because if you're familiar with geometry, which I'm not any longer, it forms the shape of an octahedron, okay? That's all I know about octahedral. The big idea behind this, though, is all of these bonds are now equivalent with respect to bond angles, okay? We have 4 things that lie in these equatorial positions, and we have 2 things that are in the axial positions. Regardless of where you are, you're 90 degrees away from everyone else. Okay, so 90 degree bond angles throughout the entire structure. Okay, all right, so we have linear, trigonal planar, we have tetrahedral, we have trigonal bipyramidal, and we have octahedral electron group geometry. So those are our basic 5 shapes, right? So how are you going to know which shape or which electron group geometry a molecule utilizes? You're going to draw the Lewis structure. That's number 1, right? Then what are you going to determine? How many electron groups are around that central atom? You're then going to look at some beautiful little table like this to tell you what the electron group geometry is, right? So if you have 2, you look at the table, you know it's linear. And it also gives you the bond angles. If you have 4, it's tetrahedral. 5, etc., and so on, okay? So that's how you're going to determine the electron group geometry. So unfortunately, that's not going to give us the actual molecular geometry, okay? So molecular geometry, which is the actual three-dimensional shape of the molecule, depends on two other things, okay? Sometimes the electron group geometry will be the molecular geometry, but sometimes it will not. And I'm going to show you the two different cases in which either it's not quite the molecular geometry or when it's not the actual molecular geometry at all, okay? So these two different cases are going to come about when, number one, we don't have equal bonds, okay? So we're going to see deviation when we don't have equal bonds. And then number two, when one of our electron groups or multiple of our electron groups are actually lone pairs and not bonds. So the presence of lone pairs of electrons on our central atom is also going to influence the overall molecular geometry. Okay, so let's start by talking about not quite equal bonds and how it actually influences the overall three-dimensional structure of the molecule. So let's start with something like formaldehyde. All right, so formaldehyde has a Lewis structure that's drawn, but I like to draw it again because I just like to draw. Okay, so if this is the Lewis structure for formaldehyde, who is the central atom here? Carbon, right? So carbon is our nice little pretty central atom, right? And if I look around my central atom to determine the number of electron groups, how many electron groups does it have? 3, right? So 3 electron groups. Remember that a double bond only counts as 1 electron group. It's a localization of electrons, okay? So if we have 3 electron groups, then what is the electron group geometry? Trigonal and planar. All right, so we have trigonal planar electron group geometry. Now, this is the molecular geometry for formaldehyde, the carbon around formaldehyde. It's going to be trigonal planar. But the presence of that double bond between the carbon and the oxygen is going to influence the overall bond angles, okay? So if we think about this double bond, how many electrons are present in this double bond? 4, right? If we consider the single bonds, how many electrons are present in those single bonds? Just 2 each, right? So the whole idea behind VSEPR is that the electrons that are present in these molecules, they are repulsing one another and they're pushing everyone else far away, okay? So because this guy has 4 electrons, how do you think its repulsion compares to the thing that only have 2 electrons in it? It's probably going to be greater, right? If you have more electrons, you're going to have more repulsion. And so what that's going to do is it's going to repulse this guy a little bit more than normal. This guy is going to repulse this guy a little bit more than normal. And what we're going to get is a bond angle that is greater than 120, because it's essentially pushing these 2 bottom guys together just a little bit more than it should, okay? So between the double bond and the single bond, we're going to get a little bit greater than 120 bond angle, which is what we see with formaldehyde. What about down here? Because these guys are being pushed together a little bit, what's going to happen to the bond angle between this hydrogen and this hydrogen? It's going to be a little bit less than 120, right? This is what we mean by not quite perfect geometry. So the presence of this double bond pushes these guys, it compresses them, and so this bond angle is a little bit less than 120, whereas the other 2 bond angles are a little bit more than 120, okay? All right, so that's easy. That's not bad. Just understand the effect of these repulsions and these bonds to understand putative bond angles from the structure. We're going to talk about the presence of lone pairs of electrons, okay? Okay, so again, we do count lone pairs as an electron group. So they're counted, but we haven't actually talked about how they influence the overall molecular geometry. So if I were to draw some sort of structure, let's say there's an X, and it's going to be bound to a Y, just imagine, and X has a nice little lone pair of electrons on it. Let's consider how these 2 types of things could actually influence the overall repulsive effects of the structure, okay? For the electrons that are in this bond, how are they distributed? are they localized centrally on one atom, or are they shared between two? They're shared, right? So in a bond, we're sharing electrons, okay? So it's kind of spread out over more space, right? What about this lone pair of electrons? Is it localized on one thing, or is it spread out and shared between two things? Just one thing, okay? So because of that, what we're going to see is the presence of lone pairs of electrons are going to essentially increase the overall repulsive effect because they're localized in one area comparatively to electrons that are localized in bonds, okay? So when we talk about repulsive effects, we're going to see a greater repulsive effect for a lone pair interaction, then we're going to decrease to a lone pair bonding pair, and then finally the less repulsive effects come from a bonding pair. And I'll try to actually demonstrate that and explain that as I go through this. Okay, so that's number one, right? So the overall repulsive effects of these lone pairs. Number two problem with lone pairs is the fact that we don't see them, right? When we look at the overall three-dimensional shape of a molecule, we're only looking at the bonds, right? We don't actually visualize or see the presence of lone pairs. So that's going to affect the molecular geometry as well. Okay, so we're going to start with derivatives of the tetrahedral geometry. So as a reminder, tetrahedral, I've been doing this all day. Okay, tetrahedral, how many electron groups were present in a tetrahedral electron group geometry? 4, right? So we have 4 electron groups. And in a perfect tetrahedral geometry, you would have 4 of them bonding, right? That's what we saw in methane, okay? Now let's say that we have something like ammonia, something like NH3, okay? So in ammonia, how many electron groups do we have around nitrogen? So we have 1 lone pair, and then how many bonds do I have? 1, 2, 3. So overall, how many electron groups are around the central nitrogen atom? 4, right? So this is what gives us this overall tetrahedral electron group geometry, okay? So 4 total electron groups. Now, 3 of them are bonding, and 1 of them is lone pair of electrons, okay? So all of this comes back to the fact that we are derivatizing from the tetrahedral geometry, okay? So in this tetrahedral geometry, 3 of these positions are going to be bonds, but this 4th position is going to be a lone pair of electrons, and it's going to be something that we don't see when we actually visualize this molecule, okay? So when we have 3 bonding, 1 lone pairs around the central atom, we do not have tetrahedral geometry. Instead, we have what is called trigonal pyramidal, because again, it forms a nice little triangle that forms a pyramid shape. Okay, so the overall molecular geometry for something like ammonia with 3 bonding pairs and 1 lone pair is this trigonal pyramidal shape. Okay. So if we go back to the perfect tetrahedral shape, what were the bond angles in tetrahedral? 109.5, right? Now I told you just a second ago that the presence of this lone pair on this nitrogen atom has a very large repulsive effect comparatively to the electrons that are in these bonds, right? So we have an increased repulsion between our lone pair and our bonds, or the electrons that are in our bonds. What's that going to do overall to these bonds down here? It's going to, again, squeeze them together. Okay, so when it squeezes them together, what's that going to do to the bond angles in something like this? It's going to decrease them. So we actually see that for something like ammonia. Perfect idealized tetrahedral geometry is 109.5, but for the bond angles in ammonia, we see a 107.0, I guess. And again, it's because of the presence of that lone pair. It's exerting this nice repulsive effect, which is essentially squeezing these and depressing this bond angle. Okay, so that's tetrahedral, right? We have 3 bonds, 1 lone pair. What happens if we move on to something like water? So water, if we draw the Lewis structure for it, how many electron groups are around the central oxygen in water? 4, right? So 4 electron groups. So the electron group geometry is still tetrahedral, except now 2 of these are bonding and 2 of these are lone. So it still goes back to this tetrahedral electron group geometry, except now 2 of these actually form bonds, and 2 of them have lone pairs that we don't see. So what would be the overall derivatized molecular geometry for this? What would you call it? It's nice and bent. Okay? So with respect to water, we tend to draw water as this linear molecule. It is not a linear molecule, right? It has a bent geometry. And again, now we've got 2 big, large, repulsive lone pairs of electrons, right? If these guys repulse one another lots, and they repulse these bonding electrons, what's that going to do to this bond angle between the 2 hydrogens? It's going to push them together even more, and so even comparatively to ammonia, we get an even smaller bond angle here because of the presence of those 2 lone pairs that are repulsing one another. So the bond angle for water, or the 2 hydrogens in water, is 104.5 degrees. Okay, a couple more things. I have 2 more geometries to talk about the derivatization of with respect to molecular geometry. So those are the tetrahedrals. We get trigonal pyramidal, we get bent, depending on how many of our electron groups are lone pairs and how many of them are bonding pairs. So now, let's talk about the derivatives of the trigonal bipyramidal geometry. So trigonal bipyramidal, as an electron group geometry, has 5 electron groups. Again, it forms this nice trigonal bipyramidal shape. So I'm going to go ahead and draw that out. We've got 2 guys in the axial, and then we've got 3 that are in the equatorial. One thing I want to note right now is that anytime you want to draw something in 2 dimensions and you want to keep it in the same plane, you can draw solid lines for that. But if I want to show some sort of 3-dimensionality to the structure, what would I try to introduce here? Dash and wedges, okay? So with respect to drawing 3-dimensional structures in 2 dimensions, in chemistry, we use something called a wedge. So a wedge is trying to show it coming out at you. Right, so we have X bound to Z on a wedge. That's supposed to show something coming out at you. And then we also use what is called a dash. And the dash is supposed to be going into the board. Okay, so again, this is supposed to be depicting 3-dimensionality in 2 dimensions, okay? All right, so 5 electron groups. We have trigonal bipyramidal electron group geometry. Now we're going to take this and we're going to replace one of these bonding groups with a lone pair, right? So there are 2 different places that I could put these lone pair of electrons, right? I could put them in the axial position, right? Or I could put them in the equatorial position. So I'm going to want to put these lone pairs of electrons in a position that's going to minimize repulsions, okay? If I put this lone pair in the axial position, how many 90-degree repulsive interactions would I have? I would have 1 here, I'd have 1 here, and I would have 1 here, right? So this would be 3 times 90-degree repulsive interactions with the lone pair. If I instead put it in the equatorial position, how many 90-degree lone pair repulsive interactions would I have? I would have this guy repulsed by the axials, but then what is the bond angle between this one and this one in the equatorial position? It's 120, right? And so for this, if I put it in the equatorial position, I only have 2 90-degree lone pair, bond pair repulsive interactions. So who would be minimizing repulsion the most? Putting it in the equatorial position or the axial? Equatorial, right? Because again, the whole purpose of this is minimizing electron repulsions. We do that when we put this lone pair in the equatorial position, okay? So that is the first derivative of our trigonal bipyramidal geometry, right? If we have 5 electron groups, but only 4 of them are bonding, and 1 of them is lone, what we end up with is something that looks like this. What does this look like? It's a seesaw, right? That's why they call it the seesaw molecular geometry, okay? So our first derivative of trigonal bipyramidal is seesaw, right? And again, we've put the lone pair in the equatorial position because it minimizes repulsion. If I want to take another bond and replace it with a lone pair, where do you think it's going to go using the same exact logic that I just did? So if I want to take one of these bonds away and replace it with a lone pair, where do you think I'm going to put the next one? In the equatorial or in the axial? So the next one will also go into the equatorial position because, again, it minimizes repulsion when we put it there, okay? So the next derivative of the trigonal bipyramidal electron geometry is something called T-shaped, right? So this is 3 bond pairs and 2 lone pairs. And again, overall, we call this T-shaped. 2 of the lone pairs go into the equatorial position. And what is this in the shape of long term? A T, right? So that's why we call it T-shaped, because we're super clever with respect to naming things. Okay, so finally, last derivative of the electron group geometry of trigonal bipyramidal. I have 3 bonds now, 2 lone pairs. What if I replace one of these bonds with another lone pair? Where do you think it's going to go? Do you think it's going to go here, or do you think it's going to go here to minimize repulsion? Back in the equatorial, right? So we just popped off that last one in the equatorial position, and we are left with our nice little pretty linear geometry. Okay, so again, with respect to this linear, we have 5 electron groups. We have 3 of them that are lone, that lie all in the equatorial positions, and then 2 of these electron groups are bonding electron groups. And that gives us this nice little linear geometry. Okay, so that's trigonal bipyramidal. What is the last unfortunate electron group geometry to mention? Octahedral, right? So how many electron groups does octahedral have? 6. 6 electron groups. If we're talking about their derivatization, right? So what are the molecular geometries that are going to come out? Let's imagine that for the first one, we have 5 bonding groups and 1 lone. And we consider the overall octahedral structure, right? The overall octahedral shape. Does it matter where we put the lone pair? No, because all of those bonds are 90 degrees, so it doesn't matter where we put it. For just logistics' sake, the way we tend to draw things, we put the first lone pair in the axial position, right? So first lone pair will go into the axial position. What we are left with is something called the square pyramidal shape, so square pyramid. Square pyramid. And again, why do you think we call it a square pyramid? Because it's a square and it forms a pyramid, okay? Square pyramidal, so that's nice. 5 bonding, 1 lone. For the last one of octahedral, we're again going to remove one of these bonds. We're going to replace it with a lone pair of electrons. Where do you think it's going to go? It's probably going to go on the other axial position, okay? So the last derivative of the octahedral electron group geometry, we have 4 of these are bonding pairs, 2 of these are lone, and what we are left with, because both of the lone pairs go into the axial position, is something called a square planar molecular geometry. Forms this beautiful little square in the same plane, so we call it square planar. Okay, so that's a lot, right? You got to think about electron group geometry. You've got to figure out how many are bonding, how many are lone. So unfortunately, there is a helpful little table that essentially summarizes and condenses all of these various structures, right? The big idea behind this table is you have to know how to use it, okay? So how do you use this table? Number 1, first thing you do is you draw the Lewis structure of the molecule, okay? You then determine how many electron groups are around the central atom, okay? After that, you determine how many of these guys are bonding versus lone, and depending on that information is going to tell you exactly where to go within the table, okay? So I have this for 2, 3, 4. On the next slide, all of the derivatives of the trigonal bipyramidal as well as the octahedral. I also give you the bond angles and the overall structures of each of these molecules, okay? So this is something that I will provide you with on the final, on the exam. So you don't have to memorize these, but you do need to know how to use it, okay? Okay, so let's go ahead. We will try this. I want you guys to predict the molecular geometry of the following 3 molecules. And it would be wise when you put this into Socrative to write everything in lowercase. Okay, so go and get your answers in, what you have thus far. Okay, so let's go ahead, we'll start talking about these. We're getting about 50% correct rate on the first one. All right, so when we're trying to predict the molecular geometry, first step is to draw the correct Lewis structure. So if I'm gonna do that, how many valence electrons do I have for this structure? I've got, how many valence electrons do phosphorus have? Does phosphorus have? So we've got 5 plus 3 times 7. How many valence electrons does that give me? 26. So then phosphorus is in the middle. I'm going to make single bonds to my chlorines and fill in the outer octets. When I do that, how many electrons do I have left to get rid of? So that's 24 distributed. I have 2 more to get rid of. I'm going to put them as a lone pair on my phosphorus, right? So then, what is the electron domain geometry, the electron group geometry? How many electron groups do I have around my central atom? 4, right? So 4 electron groups. If I ask for the electron group geometry, what would you tell me? It's tetrahedral. That is not the molecular geometry. This is the electron group geometry. For the molecular geometry, we need to take into account how many of these are bonding and how many of these are lone, right? So how many bonding groups do I have around phosphorus? So 3 bonding. And then how many of these are lone? 1. So 3 bonding, 1 lone. If you go to the table, you enter an electron group geometry. It gives you tetrahedral. For the molecular geometry, though, what is this? Trigonal pyramidal. Pyramidal. Yeah, right? Okay, good. So trigonal pyramidal, right? Again, if I asked you about electron group geometry, that would be tetrahedral. I did not. I asked you for the molecular geometry. So now, next one, ICl4. So a little bit less of a correct rate on this one. So if I sum up all of my valence electrons, I get 7 plus 4 times 7 plus 1 gives me 36 valence electrons total. Iodine is going to be in the center. I can go ahead and start by making single bonds with my terminal and all of my, or my central and all of my terminal atoms. When I distribute electrons to fill up the valence or the octets of all of my terminal atoms, I have gotten rid of 32 electrons, right? How many do I have left to distribute into this structure? 4 more. And I'm going to do that by putting lone pairs on my central atom, okay? So, how many electron groups are around iodine at this point? 6. So 6 electron groups gives us the octahedral electron group geometry. Now, how many of these are lone versus bonding? We have 4 bonding, 2 lone. What does that give us overall for molecular geometry? Square, planar. Okay, and again, it comes from the presence of those 2 lone pairs of electrons. So last one, most of you guys got this one. It's very similar to water. So for S, with 2 H's, we have overall 8 electrons. No, 2, 6, yes, 8 electrons, so 2, 4, 6, 8. What is the electron group geometry for this? Tetrahedral, because there are 4 electron groups, 2 lone and 2 bonding. And so if there are 2 lone, 2 bonding, what is the overall molecular geometry? Bent. What could you tell me about the bond angles for this molecule? They are less than 109.5, right? You know that the presence of these lone pairs is going to push those guys together a little bit more than what you would expect in the perfect, idealized tetrahedral electron geometry. Okay, so we have bent, we've got trigonal pyramidal, we've got square planar. So be competent in doing that. So a couple more things to note before we end today. For all of the molecules that we have drawn thus far, they've been very simple, right? We've had one central atom, everything else has been terminal. But as we move out and we start to get into more complex molecules, we're going to get into a question of, well, who's going to determine the overall molecular geometry, right? So for example, let's say I was trying to determine the geometry of something like this. So we have carbon that's bound to 3 hydrogens, to a carbon that has a double bond to an oxygen that has a single bond to a hydrogen, okay? So this is the overall Lewis structure for the molecule that is down here. I'll go ahead and make this a little bit more clear. Okay, so if we're looking at this and we say, well, who or how do we determine the overall molecular geometry for this molecule? The answer to that question is you have multiple central atoms in this molecule, okay? Each central atom is going to determine its overall molecular geometry, okay? So for example, if I start on the very far left, so over here, and we'll call this carbon 1, how many electron groups are around carbon 1 right now? Right, so there are 4 electron groups around carbon 1. What is the overall electron group geometry for this carbon then? It's tetrahedral, right? So this would tell you that this is tetrahedral. Are all of them bonding? Yes, right? So this, as a molecular geometry, is also tetrahedral. So if I told you that, and I said, okay, this carbon is tetrahedral, what could you tell me if I asked about the bond angles in this molecule, for these bonds particularly? They're all 109.5, right? Then, if we moved on to our second central atom, how many electron groups are around this carbon? 3, right? So we look at this carbon, this guy is right here. There are 3 groups around it, right? So what is the molecular geometry for this carbon? All of them are bonding groups. Trigonal planar. So it takes on its own molecular geometry, depending on the things that are bound to it. What would be the bond angles for this one? So perfect trigonal planar is 120, but what can you tell me because of the different types of bonds that are around this central carbon? What can you tell me about the probable bond angles with respect to this guy? Right, so we have these bond angles between the double bond and the single bond. Are they going to be a little bit more or a little bit less than 120? A little bit more, right? So a little bit greater than 120. What about this bond angle? A little bit less. Again, because the exact same idea, the electrons in that double bond are pushing these bonds together just a little bit more. And then finally, we move on to the last central atom, which is this guy, nice little oxygen, which is up here. How many electron groups are around oxygen here? 4, right? So that is a tetrahedral electron group geometry. But what is the overall molecular geometry for this one? It is bent. So we've got bent here. And again, using your chemical logic, what could you tell me about the bond angle between this guy and this guy? It's a little bit less than 109.5, right? And for water, that tends to be 104.5, so you could probably predict that it would be there. Okay, again, because of the presence of these repulsive, bulky lone pairs. Okay, so as we move out to bigger and bigger molecules, all you have to do is identify the central atoms, right? Because they're what's going to determine the overall molecular geometry. You have to identify the number of electron groups around them, and then their molecular geometry because of that, and be able to predict the bond angles coming out due to those various factors. Okay, so one more thing, and we've kind of talked about already, so this is going to be more of a review than anything. So last chapter, we dealt with bonds, right? So polar bonds, right? So if we had a bond, and I told you it was polar, how did we define polar bonds with respect to Lewis structures? What do they have to have? So what was the general thing that we utilized to determine whether or not a bond was going to be polar. So electronegativities were important, right? What was the trend with respect to electronegativities? As we move from left to right, what happened to electronegativities? They increased. What happened as we move from top to bottom with respect to electronegativities? We saw a decrease. Right? And with respect to electronegativities, this was defined as the tendency or the ability to pull electrons towards itself in a bond, right? So the more electronegative something was, the larger or the more of the electrons it was going to withdraw towards it when it was in a bond with something else, okay? So how did we define a polar bond? What did it need to have? We looked at differences in electronegativities, right? What was the requirement for a bond to be polar? It needed to be between about a 0.5 to a 1.9, right? A difference in electronegativities. And again, this was going to be indicating this unequal sharing of electrons in bonds. Okay, so now we're going to take this idea and we're going to apply it to molecules, right? Because with respect to the last chapter, we were only defining polar bonds. So now we're going to try to determine whether or not a molecule overall is polar, okay? To be polar, there are two criteria that you have to meet as with respect to a molecule. The first one is you have to have polar bonds, all right? So again, how do we know if we have polar bonds? We look at the difference in electronegativity between two things. And then second, and this is the most important one, it has to have an unsymmetrical shape, right? So what this means overall is that we have to have a net vector addition of something other than 0. And I'm going to try to explain that when we actually apply it to real molecules, okay? So for a molecule to be polar, it has to have polar bonds, and it has to have an unsymmetric shape. Okay, so let's start with something nice and easy in demonstrating this. Let's start with something like HCl, okay? So again, we're asking the question, is HCl a polar molecule overall? So first criteria, polar bonds. Does it have polar bonds? So we have H bound to Cl. Who is probably the most electronegative between these two? Cl, chlorine, right? And if we looked at the difference in electronegativities, we would find that yes, this is a polar bond. So check, you get a polar bond, okay? If Cl is the more electronegative atom, it's withdrawing the electrons towards it, right? So we're going to get a partial negative charge on the chlorine and a partial positive on the hydrogen. What is another way that I can essentially represent this unequal distribution of electrons in this bond? So I can draw a vector, right? This was drawing what we called the dipole moment for this overall polar bond, right? And when I draw the vector, I always draw it as the positive, leaving the partial positive, and the electrons essentially going towards the more electronegative element, okay? All right, so number one, for a polar molecule, check, we have polar bonds. Number two, the net vector addition of these dipole moments has to sum to something other than 0, okay? So with respect to vectors, vectors have what? They have both magnitude as well as what? Direction, okay? And so when we take this little vector here, that is representing our dipole moment in this bond, and we sum it, do we get something other than 0? Yes, right? So it has to have polar bonds, and it has to be unsymmetric. That's what I mean by unsymmetric. This has a net vector addition of something other than 0, okay? So yes and yes, if those two criteria are met, then we do have a polar molecule. Okay, so now, that's easy, right? There's nothing to even sum, there's only one dipole moment. What happens if we have something that is a little bit harder, okay? Let's consider whether or not something like CO2 is polar. So CO2, if we draw the Lewis structure, we have carbon, and the carbon has double bonds to 2 oxygens on either side, okay? Now, first one, if we're trying to determine whether or not a molecule is polar, is the question of whether or not it has polar bonds, okay? The bonds that we're looking at is between carbon and oxygen. Do you think this bond, just judging the trends and electronegativities, do you think this bond is polar? Is oxygen very electronegative? It lies to the pretty far right of the periodic table, right? So as we go from left to right, we're increasing electronegativity. Is carbon electronegative? No, right? So first check is whether or not these bonds are polar. The question or the answer to that is yes, we do have polar bonds. Again, oxygen is more electronegative than carbon. Okay, so the dipole moment that we're going to utilize for this is going to have the electrons moving towards the oxygen. Okay? Now, what is the overall molecular geometry for CO2? What is the molecular geometry with respect to this carbon? We have 2 electron groups, right? Because again, even though they're double bonds, they only count as 1. 2 electron groups gives us what type of molecular geometry? Linear. Okay. So we have polar bonds, but this is a linear molecule, right? So right now we have oxygen pulling the electrons towards it on this side. What's happening on the other side? If we're going to represent the other side by a dipole moment as well. We have the exact same thing happening on the other side, right? Because this is a nice linear molecule. When I take these 2 vectors and I sum them together, what do I get? 0, right? They cancel each other out, okay? So the second criteria to have a polar molecule is you have to have a net vector addition of something other than 0. If it sums to 0, they cancel each other, and this is non-polar. Okay, because even though we have polar bonds, the polarity of those 2 bonds cancel one another, and overall, we have a non-polar molecule. Okay? All right, so what's an easy way to check this? CO2 is symmetric, right? It has the same thing on one side as it does the other. That's generally a pretty good idea of whether or not something is going to be non-polar or not. If it's symmetric, it usually is non-polar, right? Okay, so then last little example we use is water. So water we tend to draw, unfortunately, like this. When I draw it like this, what does it look like? Do you think it's the actual bent molecular geometry? No, it looks linear, right? This is a problem. Don't be confused because it is not linear. In reality, water is bent. So now the question here is, well, is water going to be polar, right? So number one, first thing, do we have polar bonds? Oxygen versus hydrogen? Yes, oxygen is very electronegative comparatively to hydrogen. So we're getting a nice little dipole moment moving in oxygen's direction. Second check is, do these 2 vectors sum to something other than 0? So when I take my 2 vectors and I sum these, what do I get as a net vector overall? Something that pulls up this way, right? Because the x vertices actually cancel, but the y's don't. The y's add together, and we get something that pulls up overall, okay? So because of that, this is polar because it's unsymmetric, right? You can't pass a mirror through it and get the same thing, and you get a net vector that is something different than 0, okay? So with respect to this, what really influences this second criteria that we hadn't introduced until this chapter? Molecular geometry, right? How are you going to know whether or not something is going to be a polar molecule? You have to take into account the polar bonds as well as the molecular geometry, okay? So this is kind of a nice little helpful reminder with respect to vector additions. I've given you a couple of common geometries that are symmetric, so will produce nonpolar molecules, things like linear molecules, trigonoplanar, perfect tetrahedral molecules. And then I've also given you things that are unsymmetric, like bent molecules and trigonopyramidal molecules that will give you polar things overall. Okay, so just check that out when you get a chance. Okay, so I'll go ahead and stop there and hand out the exams. So overall for exam 3, the average was a 70, which was okay-ish. There is no correction to the overall score because of that. So with the second exam, I corrected the score, but I thought a 70 was pretty good for an average, so. If you have any questions about them, please let me know. Sarwar? Yes. Probably butchered.
Thank you. Joseph.
Yeah, I know. Okay. M comes before they smell. I know now. Now, very end. Nope. That's wrong. There we go. Cool. Yeah, there's scratches. Scratches.
Alan.
I should probably go.
Perfect.
Sound like SK. Davis.
Those always hard.
Can the cheat sheet be front and back?
Yep. Sarah? Yep. Valerie? Andrew?
That depends on when you're flying out. I guess I'm done on the second two at the same time. But that's okay with that. Thank you. Trips. Zelenko, yeah. Smiley face.
Yeah, sure.
Yeah, yeah, just grab a seat there before you go. I did better than that.
That's not what.
I guess I'm just gonna go for a walk.
Send out your email because I'm not avoiding the homework, I'm avoiding math.
Okay. You guys should come see me. I know all the tricks and I know all the answers too.
Wait, what did you say?
So that's why you guys should come see me. I know all the tricks and all the answers too.
So you're here all day tomorrow?
Yeah, just email me. I'm in lab. I still have all day.
So we need to come hang out with you and like I have all of my mastering homework written out on paper, I just need to go input it.
Yeah.
And
Yes, I would suggest coming to see me if you don't want to pull your hair out.
Sequence.
Sequence. R S comes after R. S.
I made a mistake all the time too. Can't look it up even.
Oh. Oh, yeah. Yes. Yeah. Yeah.
He doesn't, and he'll talk about random stuff about like when he went to school, like.
All of them, they are there, right? It's just gonna take me a second to like go and get them. I don't, it's depending on, like with this, the problem is like a lot of these, what I've done is I've broken them up to like videos, and I've uploaded different videos, so it has to go back and like piece all of this together. I'm not very organized, but that's the whole problem, so. Write me an email. Yes, I can probably for all of them, but just write me an email.
And then when you ask them an actual question, it's just like, well, it's in the book. It's in the book. Do the exercises. Well, I was like, hello, and like, I write notes. I think you.
Yeah.
See, we're.
Yeah, that is I'll have to probably tell them, yeah, so that they'll let you have it.
I think like I have to email you so that
Yeah, that worked last time though. That's
I can use the tablet too. Or like, sorry, my
your table, yeah, you can, yes. You have a question? Yeah. Yeah. I mean, you'll be fine with your class.
Yes.
Depends on what you want to score overall. Yeah. I don't know if it's drawing, it's more of shapes. So it's, yeah, it's visual, but I don't think it's drawing as much anymore.
Now I thought this just you had
Yeah.
four perfect hydrogen.
I expect it to be better on it, yeah.
Still have the perfect hydrogen bond.
Okay.
Mm.